Now let's talk about the types of equilibrium which exist in the columns. So types of equilibrium. So there are three types of equilibrium which exist in the theory of columns. So we can say it as stable equilibrium, neutral equilibrium, and unstable equilibrium. So let's define the case of stable equilibrium first. So suppose we have something like this, and we have a ball here. So a column is said to be in stable equilibrium when restoring moment is greater than the overturning moment. So let me write it. When restoring moment, we will see with some examples later, is greater than the overturning moment. So we can say okay, so this is the first case. Now let's talk about the second equilibrium position, that is neutral sorry neutral equilibrium position. So a column is said to be in neutral condition if the restoring moment is equal to the overturning moment. So we can say when the restoring moment is equal to the overturning moment, our column is in neutral equilibrium. So if restoring moment is equal to the overturning moment, then this stage is called, so this condition is called the critical stage condition. And the corresponding load is called critical load. So we can represent this condition by this easy diagram. So a ball resting on a flat plane. Now let's talk about the last equilibrium condition, that is called unstable equilibrium condition. So a column is said to be in unstable equilibrium if the restoring moment is less than the overturning moment. So this is our condition. So in order to represent this by a diagram, we can draw like this, something like this. A ball resting on this surface, on this kind of surface. Now let's talk about the elastic instability and critical load. So elastic instability and critical load. So let's understand this concept with this help of some diagram. Um, Suppose we have column like this. Okay. And sorry, this one should be like this. Okay. And here is our column here. And this column is connected to other surface with the help of some spring like this. And it has some spring constant of K. And it is further subjected to an axial loading of P. And suppose we take our position, this position as A, this position as B. Now suppose we are turning our this column member to something like this side, like here. So we can draw something like this condition. So member is going something, sorry, let me erase this thing. So member, now the new position of member is something like this. Okay. So we have turned our column members by some angle theta here, and its new position is B dash, and it's moved by some delta distance. So let me dissect the free body diagram of this scenario. So our case scenario looks something like this right now. So this is our beta dash position, and it is subjected to the axial loading P, and it is moved by some let's say delta distance from its initial position. So when we draw the free body diagram of this condition, so there is spring force acting in this direction, trying to bring back this column member to its initial position. So now this is the dissected part of this condition, this spring part, wanted to here, K. And this is our theta angle from where the column is rotated. So the spring force is given by the equation Fs equal to K delta. K is the spring constant. So we can find the restoring moment for this condition. So we can write the restoring moment for this condition as restoring moment about A is equal to mr is equal to Fs into L. So L is the length of the member. So this is the length of the member. This is the length of the member, that is L. So it is equal to the, so we can write Fs as K delta, that by substituting from here, K delta into L. So the overturning moment provided by P about A, we can write the overturning moment. Look at this diagram. Here it's P. So the overturning moment provided by P about A is given by this equation, that is MOTR is equal to P delta. So it's trying to, overturning moment means like it's trying to again bring back this column to its initial position. So let me write, this is initial position and this is final position. Okay. So it's trying to bring back the column to its initial position. So this is called overturning moment. And so when restoring moment is equal to the overturning moment, so we can call this stage as a critical stage, which we discussed earlier. And this load is called the critical load. So let's find out the critical load equation. So let's substitute the overturning moment equal to the restoring moment. So P delta is equal to K delta into L. So we can say P as a P critical delta equal to K delta into L. So P critical is equal to K L. So how should we determine, or how should we compare the P critical with the applied load so that we can determine the nature of the equilibrium? So there are three conditions. So if P is greater than P critical, then we are in unstable equilibrium. If P is equal to P critical, we are in neutral equilibrium. And if P is less than P critical, then we are in stable equilibrium. Now let's understand with the help of some examples, like some numericals from here. So the question is, suppose we have arrangement something like this. Okay. Okay. So suppose we have arrangement something like this. These are spring 1, K1, and it is connected to our column member here. Okay. And we have other spring K2 having spring constant K2 here. And it is subjected to some axial loading P here. And now suppose we have length L of this column, and this is the position A and this is the position B. Okay, so we have to find the critical load for this loading condition here. For this loading condition shown in the diagram. So let's begin by solving it, or we can say by dissecting it, because we are going to draw the free body diagram here. So let's draw free body diagram for this condition. So we have so this is our basically initial position. This one is initial position of our column. Now after this condition applied load, our column is going to have this position. Okay, so this is our, now our column will have this position, something like this. Sorry for okay, let me erase this one. Okay, let me make it more straight. So this is our condition. So we have our spring here, which is subjected to F1 here, and here will be F1, and this is B dash position, and it is moved by delta distance from its initial position, and we have further loading P here in this direction. And okay, and we have also have other load here, let's say F2 due to spring constant K2, and here's cancelling force of the spring. Okay, and this is delta position. So the first force F2 is given by spring constant K2 dot delta, that is initial displacement from its initial position, and here F1 is equal to K1 delta. So this is our free body diagram for this condition. So let me write here K2 and this is K1 here. Okay, so this is our free body diagram for this condition. So restoring moment about A. So this is our A position. So restoring moment about A, restoring moment about A is given by equation MR equal to F1 plus F2 into L. Now, where let's substitute the value of F1 and F2 in this equation. So we are going to get K1 delta plus K2 delta into L, and we can take delta as a common thing. So we are going to get K1 plus K2 delta L. Now the overturning moment about A is given by the axial loading component. So overturning moment about A is given by the equation MOTR equal to P delta. So we know that at the critical stage, the restoring moment is equal to the overturning moment. So we are going to equate like this, MR equal to MOTR. So in order to find out the critical load, we have to equate these two equations. So we can write K1 plus K2 delta L is equal to P delta. Now we can cancel delta delta from here, and we are going to get the critical loading condition, or the critical load is given by this equation, that is K1 plus K2 into L. So this is our critical load equation for this loading condition shown in the diagram.